Hello and welcome to EEE 41, Lecture 17. For this lecture, we'll cover deviations from the ideal BJT. Specifically, we'll consider base width modulation and the early voltage. We'll also discuss breakdown in BJTs, which include punch-through and avalanche multiplication. And we'll also cover some non-ideal effects for low base emitter voltages and high base emitter voltages. Also, we'll discuss the base charge and how is it related to the base transit time, and see how this base transit time relates to other parameters of the BJT. And lastly, we'll cover the hybrid pi small signal model for BJTs. So as a quick review, we have already discussed the four regions of operation for our BJT and how are these regions related to the biasing of the two junctions of the BJT. We also have shown how the BJT achieves this IV curve, specifically this IC versus VEC or VCE IV curve, in which the collector current starts increasing in the saturation region and becomes constant at the forward active region, and the achieved constant current increases exponentially with increasing forward bias of the EB junction. However, when we measure a real BJT, this is what we will actually get. So as VEC increases, instead of the collector current saturating or achieving a constant value, it actually increases slightly until it comes to a point where it suddenly increases exponentially. Now, this is related to different effects within the BJT, which we'll cover in this lecture. The first thing that causes the slight increase in the collector current in the forward active region as we increase VEC in a PNP BJT is what we call base width modulation. Now consider a common emitter configuration for a PNP where we are setting the emitter at a fixed bias or reference point, and we consider the base side to be the input and the collector side as the output, and so we vary VEC and check what is the resulting output current for a fixed bias, say IB or VEB. Now what happens within the device is that as we increase VEC, so we have here the emitter, we have here the collector, and so we are increasing this voltage VEC. And if we fix VEB, then what we are actually increasing is this voltage VBC. So as we increase VEC, we are increasing VBC. And if we do that, since the base is the N and the collector is the P side, then we are reverse biasing this junction right here. And what we know from our diode analysis is that as we reverse bias the PN junction, then the larger its depletion region, or the wider its depletion region become. And if we focus on this quasi-neutral region of the base, as this becomes more reverse biased, then this XN at the CB junction should increase, and if that happens, then the effective base width of the BJT should decrease. So W should decrease, and we're actually observing an increase in beta. So since we are biasing for a constant IB and we observed a slight increase in IC, and beta is just the ratio of IC and IB, then this actually translates to some slightly increasing beta. We can actually inspect that with the use of the equations we have provided previously. So here is the approximate expression, and we see that as the effective V decreases as caused by this change in voltage, then the denominator decreases and this beta term here should increase as expected. Now, instead of relying solely on this equation, say we want to check what actually happens within the device when we increase this, how come the beta increased? Well, that's because IC increased. So one of the things that you might actually expect is that as the effective base width decreases and with our injected holes crossing the base, and we want them to be able to reach the depletion region and the base collector junction so that they'll be swept by the strong electric field towards the collector side with the effective base width shorter, then there is less chances for this carrier right here to recombine within the base. And if that increases, then if that chance decreases, then alpha t or the base transport factor improves or increases, and beta should increase. However, if the base width is actually short to begin with, such that there is negligible recombination in the base, what actually happens here is that when W is much less than LB, then this term here should approximately disappear. And with that, we can, what will be left is this term right here. And even if there's no recombination in the base, we still expect an increase in beta because of this W term here. So we can actually simplify this if we remove this term right here. So 1 over this fraction here, so the denominator can be moved up, and so we end up with this one. And so we still get an increase in beta even if there is no recombination in the base. So that can be explained if we look at the injected holes from the emitter. So here we show the excess holes injected in the emitter side. This changes exponentially for the forward biased EB junction. And let's say for reference that we start with some VCB is equal to 0 such that there is no excess. Now as we increase VEC, this becomes more reverse bias and we get some deficit of holes at this side of the base. However, since this one increases exponentially and this one actually increases only slightly when reverse biased, then this point right here should stay relatively at the same point approximately. But with base width modulation in place, then this point actually moves slightly to the left such that the slope of the excess minority carriers at the base becomes this one. And what actually happens is that as this slope increases, the diffusion current actually increases. And that diffusion current increases IC for the same IB, and therefore we get an increase in beta. Now we can translate this increase in diffusion current and relate that with this shorter effective base width, since if we inject this the same amount of holes from the emitter to the base, then they will have to diffuse into a shorter distance before being swept into the collector. And that shorter distance translates to a shorter time to cross the base. And since current is charged over time, then the current actually increases. Okay, base width modulation is also actually called the Early effect, named after the engineer James Early, who described the phenomenon in the 1950s. And one way to describe the base width modulation or the early effect happening in your BJT is through the use of the early voltage, or symbolized as VA. As shown in this plot, as we increase VEC for a fixed IB, so IC slightly increases. And for this family of curves, we can actually extrapolate the line and see that they would intersect the x-axis at this voltage right here, which is minus VA, since this is at the negative side of the plot, although the early voltage is the positive version of that. Now, looking back, we actually say that ideally this collector current here would not increase with respect to changes to VEC. And if that happens, the plot would intersect the x-axis at infinity. And therefore, we say that for an ideal BJT, VA should be infinite. And the smaller VA would suggest that there is a large or great base width modulation happening within the device. Now, aside from affecting the DC collector current, this early voltage can also be used to describe the small signal parameters, output conductance, and output resistance of the BJT. The output conductance, G0, is defined to be the slope of IC with respect to VEC. So it is specifically the slope of this plot right here. So this is G0. And that is approximately given by this expression IC over VA. So if you look here, say we consider this point, the slope is actually the current IC over this voltage, which is slightly greater than VA. But if we have a large VA and we are limiting ourselves with some VEC that is within our supply of, say, around 3 volts to 10 volts, then that excess voltage will turn out to be small relative to this VA right here. And so we can use this approximation. For the next part, the output resistance, it is simply the reciprocal of the output conductance, and we use the symbol R0. And so the reciprocal is just VA over IC. Now, since we have an ideal VA of infinity, then our ideal output resistance is infinite, or a very large output resistance is desirable. In terms of output conductance, we want it to be very, very small. Now, we won't actually be showing or deriving the expression for VA in terms of the device parameters, but we'll say right here that VA is proportional to the base doping concentration and the effective width of the base. And we'll see at the next slide how this should make sense with respect to changes in NB and W and its effect on the base width modulation. Okay, so to reduce the effect of base width modulation, we can actually refer to this proportionality. So we can increase WB to begin with to effectively increase W. We can also increase the base doping concentration, NB, But aside from that, we can also actually increase NC. Now, how does this three options help improve VA or reduce base width modulation? So starting from increasing WB, if um, look back, the effective base width is the metallurgical base width minus the depletion regions on the two sides of the base, and if we increase this WB for a fixed doping concentration and bias, then W should increase. The second option actually improves the early voltage or reduces base width modulation, since if we have a larger doping concentration in the base, then changes in the base collector voltage would lead only to slight changes in this XNCB. And that can be easily understood if we look back at the plot of the charge density. So if we have the base side to be heavily doped, then changing the voltage across this junction would only lead to slight changes in the depletion region on the heavily doped side. However, we can actually do another thing, which is to decrease the doping concentration on the collector side. And so if that happens, then most of the changes would appear at the collector side. But we have this question right here, which is the most acceptable action? To answer that, we need to take a look back on our BJT performance parameters. And so we list them here. Starting from this first option, increasing WB. If we increase WB, then W should increase. And if this term at denominator increases, then gamma would decrease, alpha would decrease, alpha DC would decrease, and beta DC would decrease. So meaning all four of them would actually be degraded. For the next option, say we increase NB, then if we increase this NB, gamma would decrease. If we increase NB, alpha DC would decrease. If we increase NB, beta DC would decrease. And for this term right here, there is no NB, but recall that increasing the doping concentration NB would actually cause a decrease in the carrier mobility at the base because of carrier scattering. And if omega B decreases, then the diffusivity decreases, and LB would eventually decrease. And if LB decreases, then this whole alpha T will decrease. And therefore, this option also degrades all four of the BJT performance parameters. However, there is no NC right here, or there's little influence from NC. Then the best option is for us to decrease the collector dopant concentration. Again, to reduce base width modulation and improve VA. So now, aside from the slight increase of the collector current, there actually comes a point where the current suddenly starts increasing rather rapidly. So in this common emitter configuration for a high V VEC, IC will increase rapidly, either due to one of these two mechanisms, whichever among these two happens earlier. So the first one is punch through, and the second one is avalanche breakdown. Punch through happens when the EB and BC depletion regions in the base touch, as shown right here. So they already touch, leaving us with an effective base width of now 0, meaning XN at the EB side and XN at the CB side is exactly equal to W. Now we say that this is the start of punch through, which is an extreme case of base width modulation, which causes a sudden increase in the collector voltage if we increase VEC beyond this point. Now to show how this sudden increase in collector current comes about, let's look at the energy band diagram. Here we simply show EV for simplicity. So let's say this dashed line is the equilibrium shape of the line EV. And so at forward active, if this is the emitter and this is the base, then we are forward biasing the EB junction, and therefore the barrier as seen by holes should decrease. And so holes will now be able to cross the junction, or considerable amount of holes will be able to cross the junction. And aside from that, we are also reverse biasing the base collector junction to create an electric field that helps collect these injected carriers at the base. Now, as we increase VEC for a fixed VEB, then therefore we are reverse biasing this junction further. And at this case, when W becomes 0, then these two depletion regions touch, and what we'll have is this EBD or EV. Okay. However, if we increase VEC further, then we will actually pull this part higher, and what will happen is that the EV from the base emitter junction will now start to be pulled up as well. And if that happens, then the original holes that were not able to cross the barrier will now be able to cross the barrier and get injected into the base and eventually reach the collector. And that's why there is this sudden increase in the collector current beyond this punch through point. So as VCB increases beyond the punch through voltage, the potential barrier to hole injection, this one, decreases, which causes an increase in IC exponentially. Another thing that can cause the rapid increase in IC is avalanche multiplication, or the breakdown of the CB junction. So we are actually focusing on the CB junction, since at forward active it is the junction that is reverse biased and would most likely be the one that is experiencing breakdown. Now we'll differentiate the breakdown voltage for common base and give that a symbol VCB naught, and the breakdown voltage for common emitter and give that the symbol VCE naught. Now what is critical actually under these two configurations is which other current you are setting to be constant. So as we say change the reverse voltage across this junction, we expect an increase in IC, and therefore either one of the two changes. But for reference, we can actually set one of them constant, and what happens is actually slightly different for the two. So we'll start with the simpler one, and let's say we have a forward biased EB junction which causes holes for our PNP to be injected into the base and swept by the electric field at the base collector junction. However, when we reverse bias this junction enough, we can actually accelerate the carriers to achieve a very large kinetic energy that impact ionization can occur, which is the start of avalanche breakdown in PN junction diodes. And so when that happens, some holes will have enough energy to create another electron-hole pair. Now, if we focus on for the case of the holes, then the holes will just be swept into the collector, which leads to the increase in IC. And as also shown here. Now, what happens to the electron is that it is swept to the other side, meaning towards the base. Now, this is where the difference between the common emitter and the common base actually matters. If we start with the common base, then if IE is constant, then this additional electron flow should actually leave through the base. And that causes a decrease in the current IB. So since electrons are, say, going up, then the additional current by this flow is going down, and so IB should decrease. And in this case, for common base, the emitter does not actually play any role in the exchange of carriers, and this VCB naught is simply the breakdown voltage of this base collector junction if we analyze the junction separately and say imagine that this emitter base junction does not exist. And so this is the normal case of our avalanche breakdown. However, for the case of common emitter where we have a constant IB, then we don't want the additional flow of electron to be leaving the base, and therefore they will have to leave the device through the emitter, which actually gives an additional current IE. Since electrons are to the left, there is an additional current to the right, and that is also shown in this figure right here, that the additional electrons should leave through the emitter. However, there should be a balance between the injected minority carriers at the two sides of this junction, as mentioned or as consistent with the law of the junction, and therefore for each electron hole pair in the CB depletion region, this pair here, there is one electron that is able to get to the emitter, and for each electron flowing from the base to the emitter, there must be some fixed proportion of holes being injected from the emitter and into the base. And again, since the base current is constant, then this current right here should just exit the device through the collector. So this one here represents this original electron right here, and the additional current is represented by this IEP over IEN ratio, which now gives additional holes to flow out into the collector, and therefore for the same reverse bias voltage in the base collector junction, for the same amount of electron hole pairs generated, then there is more current that is produced at the collector side, and that would make the VCE not appear to occur earlier than the breakdown for the base collector junction, since for the same reverse bias we are achieving a larger increase in current, and that is consistent with this equation, since beta is greater than 1, then VCE naught is something less than VCB, and therefore VCE naught would appear to happen earlier in terms of voltage as compared to VCB naught. So next we'll consider non-ideal effects at low VEB voltages. Since initially thermal RG currents were not included in our transistor analysis, which is also not included in our ideal PN junction analysis, which we just later on added. So if we take a look back at PN junctions that is forward biased by a small voltage, so we see here the carriers that are able to cross the junction under our ideal analysis. Now, since we have here this depletion region where there is only a few carriers under low forward bias voltages, then what happens in this junction or in this region is that recombination would dominate, and the carriers that would recombine are those that would have lower energy differences, and so we'll have this additional current because of recombination. And we can also actually show that in this figure. So now there will be some additional holes flowing from the emitter into the base, but this component did not change, this component did not change, and so the emitter efficiency is slightly degraded since IE actually increased, but this additional holes will not be able to make its way eventually into the collector. So we'll modify the emitter efficiency to be this IEP. This is the original IEP over the total current at the emitter, which is IEP, IEN, and this new current IRG. And thus, under active mode operation with small VEB, the thermal recombination current is likely to be the dominant component of the base current. Since if there is only a few carriers being able to cross the junction, then the dominant current will be based on this RG component, but that current will not be able to make its way into the collector, and therefore the emitter efficiency will suffer, and eventually beta will also suffer. And therefore this RG current limits the amplification of BJTs at low forward bias voltages of the BE junction. However, for high enough VEB, then this current still is there, but is now actually a negligible component and is overpowered by the actual IEP. Okay, so here we show the currents as expected by the ideal transistor analysis, and here the additional current from the RG at the base emitter depletion region, which is dominant at low VEB or low VEB, and so they are this RG current is overpowered at slightly higher base emitter forward voltages, and so we end up with this plot right here. IB is affected. So because of this recombination thing happening here, IE will increase. This additional electron will not be able to make its way to the collector because they are just recombining at this region, and will actually have to be coming from the base, and this flow of electrons into the base adds an additional current going out, which is consistent to the direction of IB, and so we have this additional IB, but it does not affect IC. Now, the ratio is given by the distance of these two plots, since this one is already in the log scale. And this is what we actually call the Gummel plot, named after the engineer Gummel. But aside from this low VEB effects, this plot also shows the high VEB effects, which causes a decrease in both the collector and the base currents due to these effects: high level injection, current crowding, and or series resistance, which we will not anymore be elaborating. However, in general, its effect is to degrade the beta at this very high current values, and therefore there is only a, say, sweet spot or a workable range for the collector currents in which we can expect a good beta or good current gain. So here we'll introduce the concept of the base charge and base transit time. For our forward active PNP at steady state, the collector current can be written as this equation right here, assuming that W is much less than LB. And since at forward active, the base collector junction is reverse biased, then we can actually say disregard this term right here, and most of the current will be due to this term. However, we can also get this same expression from the actual diffusion current from the device. So the current IC, majority of it at forward active is due to the injected holes at the base that are able to make its way to the collector, and is described by this slope right here. And we'll be using the diffusion equation for at that point, if you may recall. So our diffusion current is minus Q AD, the derivative of P with respect to X, but the derivative of P with respect to X is just the derivative of delta P with respect to X at this W. But if there is no recombination at the base, then this will be exactly linear, and the slope at W will just be equal to the slope at X is equal to 0, or the slope of this whole line right here. So the slope is this delta PB at X is equal to 0 over W, but since this is going down, then the slope must be negative, and that would cancel with this negative term right here. Now, if you may recall, for our PN junction diodes, we can actually look at the reverse saturation current, or actually the current in any general case, to be equal to the amount of injected minority carriers at either ends of the junction, which are recombining along the way. And it can be expressed approximately as this amount of charge along one diffusion length, since that is the average distance that carriers are able to reach before recombining, and also characterized by the average time before they recombine, tau, and relate this to the actual current. So let's say this amount of charge, which is QA times LP over this delta NP, amount of charge need to be replaced every tau p, and at this side QA times ln times this delta right here need to be replaced every tau. Then that should represent the DC current as well. We can do the same for BJT. So what we'll have to get now is the charge at the base, QB, since if we assume that the injected carriers at the base from the emitter are all able to get to the collector, and that is the majority of the current, then we'll have to get the total charge at the base. So the total charge at the base is, you need this multiplier Q for every carrier, A for the cross-sectional area. The total area of this line right here, since this is a triangle, is 1/2 base times height. So the base is the effective width W, and the height is delta PB at x is equal to 0, assuming that this one is negligible. But delta PB at x is equal to 0 is this PB naught EQ VEB over KT minus 1. Now we can relate that to this current right here and say that the current IC is can be written in some form QB over tau t, but this time tau would represent the base transit time, or the time for minority carriers to diffuse across the base. Since let's say every tau, this amount of charge all of them is able to get to the collector side, then every tau in which they disappear or are able to be diffused to the other side, we need to replace them, and that should represent the current. So the difference between these two taus is that this is the time for the carriers to travel across the base, whereas this tau right here is the time for them to recombine. So this tau t is not tau b. Okay, so if we compare the two, then if we solve for tau t, then tau t must be equal to QB over IC. And therefore, we can simply get the ratio of these two. But however, since this is IC and this is QB, if we divide the two, then we need to get its reciprocal. So Q will cancel, A will cancel. This delta PB at x is equal to 0 is exactly this one. And so what will be left with is 2 dB over W squared, but the reciprocal of that is W squared over 2 dB. And so we get this expression for the base transit time. Which also sets the switching limit for the transistor, or how fast we can turn on and off this transistor. So now we'll take a look at the small signal model of our BJT, specifically under the forward active mode. So here we show, or we write, the current equations based on the Ebers small model, but we approximate for the forward active mode that this term here is negligible, since the collector base junction is reverse biased, and so we end up with this one. And for IC and for IE, this term here is approximately negligible, and so we simply end up with this equation right here. Now we'll use these two basically, along with other slight modifications to the current equations, to come up with the small signal model of the BJT. So with this, we'll try to check under some forward bias forward DC bias, VEB, IB, IC, and VEC, how the small signal components, small IB, small VEB, small VEC, and small IC are related. So the model we'll use specifically is called the hybrid pi small signal model. And for the first component, we'll try to relate what happens to this output current IC when the input voltage VEB changes by some small amount. And that can be given if we take a look at the collector current in terms of VEB. So for small changes in VEB, we'll check the small changes in IC, and to relate the two, we need to get the derivative of this equation. And so we now define transconductance. So conductance, since we are relating the output current with respect to the input voltage, and it is a transconductance, transfer conductance, since it is from the input to the output. Our symbol is GM, so G is for conductance, where M is for mutual, since we're dealing with the input and output ports. So the derivative of this one is simply itself times 1 over times Q over KT, or divided by KT over Q by chain rule. So this minus 1 term here is not actually anymore part of the derivative. However, at forward active, this term here will be much greater than 1. And so this IC is also approximately equal to this term here at the numerator. And therefore, we simply replace this one with IC and then retain the denominator KT over Q, which also tells us that the small signal parameter, just like in our diodes, is dependent on this DC current value. And it should be obvious if we look at the IC VEB plot, which is an exponential plot approximately, that the slope of the line is dependent on which point we are in the line. So for this specific IC, we get this specific slope, which is the GM of the BJT. So if we change the DC bias, GM will change, and also temperature. The next thing we'll consider is the input resistance, which can be seen if we relate the input current IB with the input voltage VEB. So we'll start with this same equation, which relates IC to VEB, but we'll use beta to relate IC and IB. So let's define the input resistance as the reciprocal of the derivative of IB with respect to VEB. So this derivative of I versus V is input conductance. So that input conductance is 1 over this R pi. Now we replace IB with IC over beta, and so the derivative of IB with respect to VEB is the derivative of IC over beta with respect to VEB, but since beta is independent of VEB for very small changes in VEB, then we'll just put it outside of the equation. And note that this derivative here is the one we obtained in the previous slide, which is exactly equal to GM. And therefore, we get that R pi is simply beta DC over GM. But if we replace GM with IC over VT, then we'll get that R pi is simply beta VT over IC, where VT is KT over Q. Now, we can also get some input capacitance. So in this model we're considering the base emitter junction as the input side, and therefore we need to get the capacitance at the base emitter junction. And so we are defining this total input capacitance to be C pi, and the base emitter junction has two components, the junction capacitance and the diffusion capacitance. So this junction capacitance is due to the depletion region, and this is the parallel plate capacitance, where this diffusion capacitance is due to the injection of charges into the quasi-neutral region. Now, since we are considering a forward active device, if we recall for our PN junction diodes, the dominant capacitance would be the diffusion if the device is deep into the forward bias region. However, for very small forward biases, sometimes the junction capacitance is still the dominant component. So although we're saying that for large enough forward biases, the diffusion component will be the dominant one, we still need to check these two. So again, the junction capacitance or the depletion capacitance is based on the parallel plate model. So epsilon A over the thickness of the oxide, which is the depletion region width of the EB junction. The diffusion capacitance, on the other hand, is related on the forward bias charge of the EB junction with respect to changes in the EB voltage. However, for a one-sided junction such as our base emitter junction, most of the charge will appear across or at the quasi-neutral region of the lightly doped side, which is the in our case the base side. So this can also be approximately be equal to the charge at the base, and this charge at the base is tau f IC, where tau f is the forward base transit time as discussed previously. And so we get this expression for the diffusion capacitance at the base emitter junction to be simply equal to tau f over gm, since we can put this tau f outside approximately, and we'll be left with the derivative of IC with respect to VEB, which is gm. Okay, so this is the hybrid pi small signal model of our PNP BJT with the small signal parameters we have discussed so far. So we have here the GM, which relates the small signal IC with respect to VEB. And note that we have indicated IB to be going out of the base terminal and IC to be going out of the collector terminal as consistent with our notation. Now this minus sign here can be applied to the direction of this voltage dependent current source, and we can actually redraw this part as this one, where we apply the negative sign to the direction, and so it is now upwards, and by KCL IC is equal to GMVEB as consistent with our expectation, since we can replace this change in IC as the small IC and this change in VEB as small VEB, and therefore we get that IC is equal to GM times small VEB, so consistent to this one, although this one should also give us the same result. Now our pi is the input resistance, so it appears here. C pi is the input capacitance, which has two components. So if we since these two are in parallel, we can say draw two parallel capacitances. One is CJBE and one is CDBE. Now we can also actually draw some junction capacitance at the base collector side, since there also exists a depletion region at that part of the device. And to indicate that in the model, we can actually draw this C mu right here, where C mu is equal to the junction capacitance at the collector base junction. So we are not anymore considering the diffusion capacitance, since the base collector at forward active is reverse biased, and the dominant component must be the junction capacitance. Now we can also include the small signal output resistance or not, which we have discussed earlier in this lecture. Again, that small signal output resistance is VA over IC, and that can be seen in the slope of our IC-BEC curve as G naught or 1 over R naught. And that output resistance must be placed at the output side, since this one relates the small signal IC with respect to the small signal VEC. For completion's sake, we include here the version of the hybrid pi small signal for NPN. The major change is the direction for the base and collector currents as defined, which is consistent with our symbol where IB goes into the device and IC also enters the device. Now there must be no problem with this change from VEB to VBE, since this is still the base and this is still the emitter, and this is VBE of course. And if we simply take the positive terminal at the emitter, then we should name that as VEB. So there's no critical change here, there's no change here, there's no change here. At this output side, this is VEC simply because we take the positive side at the emitter. So now that we need VCE, we just take the positive side at the collector. So there's no critical change here. This is just the same. Now, these two right here might look different, but they are actually the same, since although we have this minus sign right here, but this one is in VEB, and therefore if we apply that minus sign to this voltage, we'll just get this VBE. Now, in terms only of the circuit components and how they are described, if we focus only on this portion, then we can say that the hybrid pi small signal model for NPN and PNP are exactly the same. The only difference is the default direction of the currents. So you can actually remember just one among the two and use that for either NPN or PNP, although it will be easier to remember this one, since there is no negative sign. So here we just define the cut-off frequency or the transition frequency, or sometimes called the transit frequency of the transistor, and we denote that as F sub t, which is equal to omega t over 2 pi, since omega is equal to 2 pi f. Now, how do we determine this ft? So ft or ft is the frequency at which the small signal current gain or small signal beta will be equal to 1, and beyond this frequency there will be no more current gain, and we'll expect that this transistor cannot anymore amplify our small signals. So we'll just need to determine this omega t, where IC is equal to IB, so we get this 1 with the help of the capacitances, or based on the capacitances of the transistor. So here we set up an equation to help us determine IB. So VEB is simply I times R, or in this case the impedance, which is the parallel of R pi and 1 over j omega c pi, and therefore we can consider this whole thing as z pi and end up with an equation VEB is equal to IB z pi, where z pi is equal to, since this is impedances in parallel, 1 over R pi plus 1 over j omega c pi, or simply j omega c pi. And so we end up with this equation right here. On the other side, IC is simply equal to GM VEB. Since again, we can remove this negative sign and apply that on this side, so this current source will now be directed upwards. But when we characterize the output current, we need to short the output side, since for a current source, the no load case is when you short the output side. So there is no power delivered at this portion. And since this one is shorted, there is no current here, there's no voltage here, and there is no current here. And so IC is equal to GM VEB. And since omega t is when IC over IB is equal to 1, then we'll just take the ratio of the two. So IC is equal to GM VEB, and IB is equal to this term times VEB. So the VEB cancels, and so we get this one and get the magnitude of the complex denominator, and then replace R pi with beta over GM, and C pi to be CD of the BE junction and CJ of the BE junction. So to make things easier, we can just cancel out the GM at this the numerator and the denominator. But to do that for the last term, we need to multiply by GM over GM. And so we cancel the GM terms. And so we are left with 1 over 1 plus beta plus j omega tau plus Cj over Gm, which is Kt over Q over Ic. This is the same equation here, but since we want the ratio to be 1, then this is already 1, and therefore this thing at the denominator must be equal to 1. And the magnitude of a complex number is the real part squared plus the imaginary part squared. And we want that to be equal to 1. But since we have here 1 over beta DC, so this is at DC, and and this is something we expect to be somehow large, then this should be small. And if this is small, something's small squared is much smaller. And so we need this term here to be equal to 1 approximately. And if this is equal to 1, then omega must be equal to 2 pi ft, equal to 1 over this thing. And so we are able to get this expression for the transit frequency. Meaning if we want to increase the transit frequency, then we need to decrease tau f, meaning we need to decrease this effective width of the base, or we can decrease the junction capacitance. Although aside from that, we can also instead increase IC. So this means that to get a higher transit frequency, or to be able to operate the transistor at higher frequency and expect it to still amplify, then we need a higher current IC, or we need to pay with some power consumption. Now for the full BJT model, we include this CJBC, RE plus RC term, which wherein CJBC is the one we mentioned a while ago to be equal to C mu, whereas RE and RC are the series resistances associated with the emitter and the collector terminals. So to maximize FT, we need to increase IC as mentioned a while ago. Although as we increase IC, the series resistances will start to kick in, and the high VEB effects will also start to kick in, thereby reducing beta as well. So we can expect that FT will not continually increase with IC. We can also minimize CJ for both junctions, minimize the series resistances. So when we make this thing smaller, FT will increase, or minimize PF again by decreasing the effective base width, or aiming for a higher diffusivity at the base, meaning there must be minimal traps at the base, or sorry, minimal scattering at the base. Okay, so in summary, this is the small signal model for our PNP because of this direction right here. But if we focus here, this should be the same for PNP or NPN, and we can replace this negative GMVEB as simply GMVBE while still retaining this direction. GM is IC over VT. R pi is equal to beta over GM. R naught is VA over IC. C pi has two components, junction and diffusion. The junction capacitance is the depletion capacitance, which is the parallel plate form, whereas the diffusion capacitance is based on the base transit time. We can also include in this model C mu, which is the junction capacitance at the base collector junction, and series resistances RC, RE, and also sometimes RB. And that's it for this lecture. Thank you very much.